Welcome to the presentation of statistical characterization of random errors present in Synchrophasor measurements. Sponsored by Arizona State University, my name is Demetra. So let me take a step back and take a little bit of time to talk about the background and preparatory work needed to execute this experimental design. Noise is present in phasor measurement units, or PMUs for short. Actually, noise is present in all electrical devices. But for PMUs, it can potentially be detrimental to the accuracy of their measurements. Recent research endeavors have tested PMUs while they are operating in the field. However, due to other electrical systems and environmental factors, this might not be the most accurate way to measure the noise in phasor measurement units. Rather, at Arizona State University, we have created a controlled laboratory environment to test these Synchrophasor devices. Using the Fluke 6135A calibrator to pass controlled time-synchronized electrical waveforms into the device under test, or DUT for short, we can accurately produce comparable waveforms across both the input and output terminals of the phasor measurement unit. We've also created Python script that can accurately identify the noise as either Gaussian or non-Gaussian by running statistical analysis and mathematical analysis against the incoming data. It also produces a histogram, which can very quickly visually indicate whether or not the curve is Gaussian to the human eye. For testing, we've tested both phase modulation and amplitude modulation, as well as frequency ramp ups and frequency ramp downs. For the simplicity of this experiment and this presentation, we've decided to show the phase modulation results as well as the frequency ramp down results. Now note, the x-axis indicates the degrees off of the nominal value in all four of the following histograms that you're about to see. So let's go ahead and take a look at the phase modulation results. Looking at both a P-class and an M-class device, we can very quickly visually tell that neither are Gaussian. The P-class device shown on the left side of your screen indicates the phase error for that P-class, and it indicates a bimodal distribution. One peak at a lower nominal value, a valley in between, and another peak at a higher nominal value. Meanwhile, the M-class device gives another distribution, a 5 beta peak model. Now, visually, again, we can tell that neither are Gaussian, and statistically and mathematically, the numbers back up that neither of these curves are Gaussian. So let's go ahead and take a look at the frequency ramp down in comparison. Now, looking at the P-class device, you might be tempted to say that it's roughly Gaussian. We do have a normal curve with a peak in the middle. However, both the mathematical analysis and the Shapiro-Wilks tests, the statistical analysis of the Shapiro-Wilks and the Kolmogorov-Smirnov tests, both indicate that that P-class result for the frequency ramp down isn't Gaussian either. For the M-class device, by comparison, each of those individual peaks themselves are Gaussian. However, all three combined produce a result that isn't Gaussian in itself. We're looking to do further research and testing across all four of the results, frequency ramps, ups and downs, phase modulations, and amplitude modulations. But for now, this is just a quick snippet of what's further expounded upon in our paper. Our final results indicate that the majority of the tests produce noise errors that aren't Gaussian by visual inspection, statistical analysis, and mathematical analysis. Our intention is to create further testing, such as regression models to identify potential noise errors due to outside factors, simulating the PMU behavior on a power line, such as varying multiple factors at once still within our controlled lab environment, and further tests to identify the behavior between newly made models and products that have been previously utilized, trying to see if there's a difference there as well. I thank you for listening to our presentation, and I hope that you enjoy the rest of IEEE PESGM 2021. Thank you.